Okay, now I'd like to talk about a dynamic programming solution to this problem, which is iterative. And so we won't have any recursion. And we're going to do it just like we always do with dynamic programming. We're going to do it bottom up instead of top down. So the recursion is going top down. It's starting at the full problems and breaking them down into smaller. We're going to start the smaller problems and move up. Now, one thing that's kind of nice is we can actually kind of use a lot of the code that we already have here. But instead of making recursive calls, we're going to look things up in a dynamic programming table. So what I'll do is I'll say table equals empty.zeros. Let me make two variables to hold this. So I'll say m is length of the first string, n is length of the second string. So I'll make a table of all zeros, m, n. So it starts off saying the best I can do is not matching anything. All right, and like I said, I'm going to start bottom up. So I'm going to go start with m equals 0, n equals 0, and build up from there. Okay, so let's see, what can we do to this code? Well, I don't need this anymore. I guess I'll just say no, I don't need this at all because I'm looking at the first character now. So each one of these would have at least one character. So now it's not s1 negative 1, it's actually s1 if s1 at index I is equal to s2 at index I. So now we're going to be storing a result. So the result is going to be the maximum, the length of the maximum common subsequence. So here I'm going to say, yeah, if the character at index I in the first string is equal to the character at index j in the second string, then I do this. Now I will be looking at, this will actually be the table at index I j minus, no, sorry, table at index I minus 1, j minus 1, because I chopped the last character off of both of those. I gotta be careful about this because actually, you know, this could be out of bounds depending on where I am. So I should make sure that you know, if they match, I'll say that the result is 1. But I will only add this if I'm not going to go out of bounds. So I'll say if I is greater than 0 and j is greater than 0, res plus equals that. Okay, so I just did the same thing that I did with the recursion, but now I'm doing it iteratively using the dynamic programming table. And I kind of baked in my stopping condition naturally with this if statement. Alright, so now in the else statement, I am going to do something similar. I need to consider two things. I'll say res1 equals 0, res2 equals 0. So res1, so if I is greater than 0, then I can make res1 be the table at I minus 1, 0. So that's chopping 1 off of the first string. And then I'll say if j is greater than 0, res2 is equal to table at I, oops, I meant to say I minus 1 j. So go to I j minus 1. Okay. So look, this matches the recursion here. The first recursive branch, I was chopping 1 off the end of the first string from where I was. So that's I minus 1. Second branch, I was chopping 1 off of the second string from where I am. So that is j minus 1. And so then the result would be the max out of these two. All right. And so once we're finished all these cases, we really have 3 cases. We're either going to chop off the last 2, we're going to chop off 1, or we're going to chop off the other. Out of the 3 of those, we'll then store which one made it through. So we'll say table at index I, j is equal to that result. Now we've got an entire dynamic programming table. We can just return the last element, because that'll hold the solution we want. All right, let's see. Does this work? Okay, I need NumPy. I was making this table here. Okay, 3. Actually, we know this is going to be an integer, so well, I can do table is dtype equals int. Okay, fine. I didn't like the 3.0 there. What about this phone versus phones? Okay, that still seems to work. Okay, now we have code that's efficient enough to work on a longer example. Naive recursion without memoization wouldn't work. Memoization, that would work, but here we're doing it with dynamic programming in a bottom-up fashion. So if I look at the length between these two, of the common subsequence, I get 16. Now what's interesting is rules are great with all the spaces in there. That's only 15 characters. So somehow we actually found a subsequence that is 1 character longer in common between the two. So you're going to implement now, you're going to remember, so I'll start this off here. There's going to be a memory that remembers what choices I made at each step. So I'll say that, it's 0 by default. That means I go diagonally. But if I choose to chop off just the last character of the first one, let me make that a 1 by convention. So I'll say choices I, j is equal to 1. If I choose to chop, oh yeah, and I have to say that's if that one won out. So if res1 is greater than res2, then choices I, j equals 1. Else we'll just break ties arbitrarily for our ties. Choices I, j equals 2. That's what we'll say. So if we choose the first path here to chop, if we find that the best thing to do was to chop off the last character from the first string and keep going, we'll say that was a 1. If we find that the best thing is to chop off the last character of the second string, well then we'll call that a 2. So now we have all these choices. The only other thing is if we're down at a length of 1 on the first string, then we're going to have to chop things only from the second string. So that's the first row. So I'll say the entire first row. This is a slice in a 2D array in NumPy. The entire first row should be 2. And by the same token, if I'm in the first column, that means that there's nothing left to do to my second string, so I better only chop things off of the first string. Okay, so let me just look at this on a simple example, and then you'll write the code to backtrace. Oops, I meant to be a 0. So if we look at this on, let me just make this a little simpler again. Phone versus phones. Let's look at the choices. So basically we're told that we should keep, so we start at the end, we should keep chopping off both characters. No, 2 says chop off of the second one. Okay, so I chop off the second one. Then I keep walking diagonally, that's a 0, until I get back here. And I'm done actually, once I get back to the beginning. Okay. So that is how that works. So you can complete the backtracing and you'll actually find out, cliffhanger, what is the common sequence? If it's not rules are great, what is it? Rules are not great, I guess, is what we're finding here. There's something else which is a little bit gibberish, which matches a little better between these two. Okay, so that's it for that.